...400 years ago, in the beginning of the 17th century, Galileo Galilei initiated a new dialogue with the universe. Galileo Galilei invented the telescope, and it was called a spyglass at the time. And he showed this to the Doge of Venice, and the Doge of Venice was extremely interested in Galileo's invention, because through Galileo's spyglass, he could see the ships arriving in the Bay of Venice 2 hours before you could see these ships arrive with the naked eye. But Galileo decided to use the spyglass, what we now know as the telescope, for something different altogether. Galileo pointed it to the skies, to the moon, to Jupiter, and so forth. And in doing so, Galileo found the first observational evidence for the Copernican model, for the idea that not the Earth is the center of the universe, but that the solar system goes around the sun. And you know how he conveyed that message? The very first observational evidence for the Copernican model, this is what he wrote to his friend Johannes Kepler. The mother of loves emulates the shapes of Cynthia. The mother of loves is Venus, the planet Venus, and Cynthia at the time was the moon. The fact that Venus has, when we look at Venus, has phases just like the moon, was in fact the very first piece of observation that could not be explained by the old Ptolemaic world model with the Earth in the center. And so that was Galileo's dialogue. He wrote a book, a dialogue between two world systems. One, the Copernican theory, the other one, the old Ptolemaic model. Now, Galileo was first working in the state of Venice, Padua, Venice, but then decided to move to Florence, which was much more under the auspices of the Vatican. And so his work, as you know very well, did not go down very well with the church. In fact, he wrote a famous, and in the end, this book was banned until 1835, so 2 centuries later. That was too bad. But the interesting point in this story is, of course, that Galileo's decision to point the telescope to the sky and to rethink, to look at the universe and rethink our world model, had epistemic foundations. It was an epistemic shift in the way we view our existence. And so he wrote a famous letter to Christina de Lorraine, in which he wrote that famous sentence, "The intention of the Holy Ghost is to teach us how one goes to heaven, but not how heaven goes." Why am I telling the story of Galileo? Because, believe it or not, we are in the midst of a Galilean revolution in astronomy right now. And that's what I want to explain you in the next 35, 40 minutes. And that has everything to do with, as Julien already pointed out, the Einstein Telescope. Now, the Einstein Telescope is a dream at this point. It's a moonshot project. It does not exist yet. Furthermore, it is by no means a normal telescope. It sits, to start with, it's gonna sit underground, deep underground. It's a telescope not for light. It's a telescope which has a triangular configuration, sort of an observatory with laser light, and those laser lights are used to measure gravitational waves generated deep in the universe, which go right through everything, right through the Earth. Now, the Einstein Telescope is a big science project, so it involves scientists and engineers from all over the world. But you see sort of where this star of Einstein Telescope shines, where the nugget of the whole project lies. In fact, And that's also where the whole strategic and socio-economic dimension of this project comes about. The Einstein Telescope, we hope to build it around the corner. We hope to build it in what is called the Euregio Meuse-Rhine. This is the Euregio Meuse-Rhine. It's not a country. It's a border region between the Netherlands, Belgium, and Germany. It covers a few provinces. And it so happens that in the midst of the Euregio Meuse-Rhine, in the Voerstreek, you find underground this yellow band from Liège to Aachen, which is called the Bose-Valdieu block. And it's a fairly rare geological structure, which consists essentially of a soft top layer, sand, 100, 150 meters of sand, and underneath fairly hard stone, sandstone, limestone, older, much older stone. That's the kind of underground we need to build Einstein Telescope as an observatory. We need the soft layer in order to damp all earthly vibrations, and we need the harder layer underneath in order to construct this giant observatory in that layer. And you can see it's not ideal, Einstein Telescope being a triangle, each side about 10 kilometers. We're managing to put two caverns, 2 points in the Bose-Valdieu block, but the third one, and this is where we are currently drilling and putting sensors in there, the third one is fairly dangerously close to the E40 and the TGV from Liège to Aachen. So it's not a done deal yet. It is not completely certain yet that the underground in the region will be appropriate, but the first measurements, the first seismic measurements, the first drillings seem to tell us that it should be possible. Let me say up front, we're not the only candidate to build the Einstein Telescope. There's one or two competing proposals, one from Italy and possibly one from Saxon. But we can talk about that later. Now, why is this called the Einstein Telescope? It refers, of course, to Albert Einstein. Here is one of these rare portraits of Einstein made by the so-called Einstein painter, Blomme, when Einstein was essentially a refugee in 1933 in Ostende. Einstein, in 1915, wrote down a famous equation. This is not Einstein's hand. It was pure maths at the time. And this equation, it's this equation which encapsulated his general theory of relativity. It's a mathematical equation, and it's easy to read. We're going to read it together. All right? It has a left-hand side and a right-hand side, like all equations. On the left, we have a mathematical object that represents the structure, the geometry, the shape of space. On the right, the T represents the stuff inside the universe. Planets, stars, dark matter, whatever you want. And the magic of Einstein's equation, the magic of Einstein's insight is, of course, the equal sign in the middle. It tells us that the shape of space on the left is tied to the stuff inside the universe. And that dialogue, that interaction, that is what we call gravity, according to Einstein. For the philosophers, the epistemic twist encoded in this mathematical equation is the left-hand side, right? The shape of space. This was metaphysics before Einstein. This was just a static metaphysical arena in which everything else happens. Einstein says, no way. Also, the shape of space is part of science, part of physics. And this is the equation with which Einstein took the shape of space out of its metaphysical context. And so this is how gravity works, according to Einstein. The mass of the Earth creates some sort of valley in the invisible fabric of space in our neighborhood. And that valley keeps an object like the moon nicely in orbit around our planet. The same thing with the sun. The sun creates a valley, keeping the planets in orbit around it. So what's gravity? Gravity, according to Einstein, is a manifestation of the shape of space. It's not some sort of magic force like Newton had it. This is the way how the Earth and the sun communicate, through the empty space in between them. And so just a few months later, Einstein realized, but wait a minute, if space can bend and curve and all that, then surely space must also be able to vibrate. If I have two objects and they're in motion relative to one another, well, the fabric of space is going to have to respond, and these are these gravitational waves that Julien already mentioned. But I have not explained you one thing in Einstein's equation. Relating G, the shape of space, to T, the matter and the energy, the relation involves what we call a constant of nature, 8 pi g over c to the fourth. Now, you remember from high school, 8 pi g over c to the fourth is damn small. It's extremely small. It's 10 to the minus 35 or something. So this means that you need an enormous amount of matter to slightly change the shape of space, curve space-time. And that's the reason why Einstein said, all right, these gravitational waves, they must exist in the theory. Einstein made space and time come alive, so to speak, waves, vibrations, but we're certainly never going to be able to detect those gravitational waves. They're far, far, far too weak. And so here you have it. Two black holes orbiting, colliding, and sending the energy into a burst of gravitational waves. Those gravitational waves are invisible ripples. There's not a single particle involved. And they go right through everything at the speed of light, through stars, through planets. And a ripple of space, what can a ripple of space do? It can't do anything else than just change the length of things. This is exaggerated, of course, but you get the idea. When a burst of gravitational waves passes through the Earth, lengths, distances are just slightly changed. But because of the weakness, because of the small amplitude of those gravitational waves, you need these very strange observatories. You need these observatories, a new kind of telescope, in which you are essentially monitoring the length of 2 or 3 sites. This is an existing observatory, which was at the heart of the Nobel Prize in 2015, and the length of these tubes is about 4 kilometers. Now, I mentioned that Galileo's new dialogue came about because there was like an invention, the invention of the telescope. You might wonder, what is the key invention that makes it possible today to open up a new dialogue, a la Galileo, by measuring gravitational waves? And I think the key invention is the fact that nowadays we can manipulate light. We can control light to an exquisite precision and use this as a tool to measure lengths, to measure distances. This is what's happening inside this observatory. You send in a precise laser beam. You let the beam split, and you put a mirror at the end of each tube. It bounces back, and you fix things so that both beams annihilate one another perfectly, except when a gravitational wave passes. That will change the relative length of these two arms, and a slight laser signal will escape. That's the measurement of a gravitational wave. And that's the measurement which was performed successfully about 10 years ago in these L-shaped observatories in the United States. That's the famous Nobel Prize-winning plot. Here you have time on the horizontal axis. Here you have frequency. You have the two observatories. On the 14th of September 2015, in both observatories simultaneously, as for a fraction of a second, laser light escaped. Not quite perfectly simultaneously. Why? Because gravitational wave moves at the speed of light. One observatory is in the south, in Louisiana, and the other one is in Washington. So it did take a small fraction of a second. And this is the kind of signal we saw. The next question is, well, all very nice. How do you read this? That's all you get. How do you read this? Well, to read gravitational wave observations, you've got to go back to the mathematical equation of Einstein, to Einstein's theory. You put in a set of matter on the right, and you figure out what's going on the left. The gravitational waves are encoded in this mathematical equation, and they follow some sort of pattern. When the objects are far away, the frequency is small, then the frequency rises. There's some sort of very complicated merger phase, and then there's what we call the ring down phase. The new object settles down. Now, Einstein's equations, for the mathematicians among you, are a set of 10 nonlinear coupled differential equations. Even with the computer power today, we cannot solve these equations in general. We muster a huge amount of computer power just to get a handle on specific situations. That's the field of numerical scientific computing. It's a field, in fact, which was pioneered in 70, 80 years ago, here in Belgium, in Leuven, by Georges Lemaitre. Georges Lemaitre, in the 50s, bought one of the top computers at the time and established Belgium's first laboratory for numerical computing. Here you see Georges Lemaitre. So who is this? That's André Bartholomé. You must know these stories, Les Calculatrices. There's a whole list of excellent, brilliant, famous, not famous women behind many of these computer simulations in those days. You have the women behind the moon landing of the NASA, who were calculating the trajectory of the rockets. You have famously the women behind the Enigma project of Turing in the Second World War, and so forth. Lemaitre also had an assistant, André Bartholomé, who was an expert in programming this old computer to calculate trajectories of particles in the cosmos. The first actual numerical simulations of Einstein's equation were done in the 60s. They were done at IBM, at a time when IBM still had a proper science lab. Nowadays, of course, what have we done in order to be able to read the gravitational wave signals? We have systematically simulated all sorts of collision events between black holes and neutron stars and so forth. We have essentially established a library of possible cosmic events that could be out there. And each time, calculating the pattern of gravitational waves emerging from such a collision. And at that point, it's just a matter of pattern matching. You have in blue what you observe, in yellow you have your library of simulations, and you run through your library of simulations until you find a match. You vary the masses of these black holes, you measure their distance to the Earth, you measure their inclination, their rotation, and so forth, and eventually you find a match. And so the Nobel Prize observation of 2015 turned out to be a gravitational wave signal of a fraction of a second generated by the collision of two black holes, each one 30 times the mass of the Sun, 1.3 billion years ago, in the direction of Virgo. That was the result of that observation. By now, and that's the Galileo moment, this is an observational run. That's now how we look at the cosmos. You have these gravitational wave bursts arriving, we put them on sound. These are black holes colliding in this galaxy or that galaxy, 1 billion years ago, 10 billion years ago, you name it. The cosmos, it's as if we have developed a new sense to explore the universe, just like Galileo invented the astronomy based on light. And so it's becoming a lot of fun. Once every few days, as you can see, this is the date of that observation run. This is the third observation run, which happened in 2019. And here, one of the detectors was not functioning, and then it was functioning again, and you see these black holes keep on colliding, and you see it's always a beep. The frequency rises because the black hole come closer together, and it quickly dies out. Even during COVID, black holes kept colliding. So what can we learn from listening to these gravitational wave bursts of black holes? Well, there's this tombstone of Hawking in Westminster Abbey, right? It has an equation. T stands for the temperature of black holes. And the equation has a prediction. The equation Hawking wrote down in 1974. In fact, and he wanted that equation on his tombstone because it's as magical as Einstein's equation. It's the very first equation in all of physics, even today, which has all these different constants of nature united. H is the Planck's constant, quantum theory, C is the speed of light, G is Newton's gravity constant, M is the mass of the black hole, K is Boltzmann's thermodynamic constant. There is no other equation in all of physics that has all these macro elements, thermodynamic elements combined. And the equation suggests that black holes, contrary to what Einstein thought, are not just empty holes in space-time. The equation suggests that even black holes must have some internal structure, but we don't know what it is. And Einstein's theory doesn't tell us what it is. It's a glimpse. This equation is a glimpse of physics to be discovered in the future. It has one observational consequence, this equation. And the observational consequence is that if two black holes collide, the new black hole that forms will have a surface that is larger than the sum of the surfaces of the initial black holes. And of course, when Hawking was still alive in 2015, and immediately he asked us that question. Well, so is it the case? And sure enough, all these black holes, all these popping black holes that you've heard, satisfy this equation. But the current observatories have not given us any hint. The current observations have still not given us any hint of the deeper meaning of this equation. So what is there? What's the structure of black holes if it's not just empty bits in space-time? That's the kind of question for which we need the next generation of observatories, Einstein Telescope. Einstein Telescope is going to observe thousands and millions of collisions. Right now, we only see the top of the iceberg, if you wish. Einstein Telescope is essentially going to take us right to the edge of the observable universe. Now, what's the difference for the engineers among you then between the current observatories and Einstein Telescope? Well, for one, Einstein Telescope will be under the ground for reasons that I explained, so you damp vibrations. Secondly, it's going to be operating like CERN in a cooled vacuum structure. So it's going to be operating at cryogenic temperatures well below zero. And thirdly, at the end, you've seen in this simulation that I showed you, at the end there are these mirrors. Now, these mirrors, so you bounce back and forward this laser beam. The laser beam goes at the speed of light, so the time it takes the laser to go back and forward, you know the speed of light is a measure of the distance of this thing. But that's only going to work if the mirrors at the end hang perfectly still. They should be isolated from all earthly vibrations, and so that they're sensitive, so that the distance is only sensitive to cosmic bursts. And the way you hang these mirrors is it's both simple and complex. It's simple because it's physics which was known in the 16th century, and complex for reasons that I will explain you. That's the mirror. And in fact, in Einstein Telescope, we're going to hang these mirrors off a series of 4 or 5 pendula, each with different lengths and each with different masses. And you know from high school that if I move this slow, then the mirror moves with me, with my hand. But if I move this fast, the mirror hangs still. And so in an ingenious chain of pendula, you can in fact eliminate a range of vibrations which leave your mirror hanging perfectly still. That's essentially the basic, very simple principle, but extremely difficult to put in practice. Why? Because of this weakness of gravitational waves. The distance over 10 kilometers, when a good gravitational wave passes, that distance changes by a much less, by 1,000 of the diameter of a single proton. So the gravitational wave, you're trying to measure something like a precision of 10 to the minus 20 or 21. No wonder that Einstein thought this is not going to work. Galileo was surprised. He points his spyglass to the moon, sees all these craters. He points it to Jupiter. He finds there are all these moons around Jupiter. And over 400 years, we have been surprised many times through astronomy, through electromagnetic astronomy. We've discovered many other galaxies than the Milky Way. We've discovered that the universe expands. We've discovered all sorts of things. And yet, the visible stuff in the universe only makes up 5%. Most of the universe is dark. It's governed by dark matter, black holes, particles we don't know, dark energy, and so forth. So we have every reason, now that with these gravitational waves we are unlocking this dark side of the universe, we have every reason to believe that we should be surprised again. Now, just to refine this statement, it's not that the visible and the invisible side of the universe are completely independent, right? Visible stars collapse to black holes. That's a transition. And also, imagine you have 2 neutron stars colliding, then that process will emit gravitational waves. That's the purple thing, but it also will create a giant explosion. And this was perhaps the most amazing observation with these observatories today. It was an observation which was made by the gravitational wave observatories, but also by normal telescopes. And the gamma radiation, the high energy end of the electromagnetic spectrum, arrived from this collision exactly at the same time as the gravitational waves. providing for the very first time observational evidence that Einstein was right to think that gravitational waves move at the speed of light. You should be interested in these collisions. Certainly those among you who are interested in gold and silver, because it's those kind of collisions that filled the second half of the table of Mendeleev right for us to use. The first half of the table is filled by normal nuclear fusion inside stars, but the second half, beyond iron, is very difficult to fill. That's done in these collisions of neutron stars and then spread out through the universe. Now, I should say that Einstein Telescope is not going to be the only instrument. Just like you have light waves of short and high frequency, from infrared to X-rays and gamma rays, same thing with gravitational waves. They are produced in all sorts of frequencies. And with this pendula of Einstein Telescope, we are sensitive to a particular frequency band. It's like constructing a telescope for visible light, say. In parallel to Einstein Telescope, there's another project going on, led by the European Space Agency, and it's based on the same principle. It's a triangle, but up in space, where there's no worries about vibrations. In 2035, ESA will launch a rocket. And inside that rocket will be 3 satellites, and those 3 satellites will be spread out into space. They will be trailing the Earth, and each of these satellites is equipped with a laser. They will form a triangle, each side 2 million kilometers. It's the biggest experiment ever conceived. And together, these satellites, in their triangular configuration, they will orbit the Sun, creating a huge disk. When gravitational waves pass through the solar system, these satellites will move with respect to one another. That's the complement of Einstein Telescope. Einstein Telescope is roughly based on the same principle, but because the triangle has to fit under the ground here on Earth, the size, of course, is much smaller. Probably Einstein Telescope will have sides of about 10 kilometers, and so it's going to be sensitive. Just like with normal telescope, the sky looks differently depending on the frequency with which you look at the cosmos. So it's these two together which, in fact, will unlock this entire universe through observing gravitational waves from all sorts of collisions, probing back to the earliest moments. So here you see the history of the universe. Here we are today, and we've mapped out a history based on that 5% of visible stuff. The 21st century is going to be that era in which we're going to write this history once again, all the way to the era before there were even stars, all the way back, I would say, to the Big Bang. With visible light, with normal telescopes, this is a boundary, this is a horizon. The earliest stages of the universe isn't even transparent, right? You can't see through. No matter what kind of telescope you will ever invent, you're not going to see through these first stages. It's like trying to see inside the sun. But a lot is hidden in these first stages. So these gravitational waves are really unlocking new regions, new unexplored regions of the universe. And of course, ultimately, so you might say, well, you might ask, what is the real, most fundamental reason I can think of why we should build this Einstein telescope? And I think it has to do with the beginning, with the earliest stages, with the unexplored realm right there. You see, what happens in these earliest stages, if you go back to Einstein's equation, when you run back time, all the Milky Ways, all the galaxies, eventually end up on top of each other. So it's a curious feature of Einstein's theory that the universe just can't stand still. when it must expand. So in the past, space itself, the left-hand side of the Einstein theory, contracts. And with that contraction, space also takes down time. So the Big Bang, which we're approaching here, the Big Bang is not an explosion in a space that already exists. No, it's the beginning of space and time. It's that moment in the past where the fabric of space just disintegrates. That's another epistemic moment, in fact. So this was essentially a discovery of Euregio Meuse-Rhine. And interestingly, when confronted with certain skepticism, both by the scientific community and others, he paraphrased Galileo. Euregio Meuse-Rhine, in 1931, after discovering the Big Bang, wrote, well, once you realize the Bible does not purport to be a textbook on science, the old conflict between science and religion disappears. But then he added, because you could ask, well, okay, what happens then at the Big Bang? And he had this truly interesting but far-off intuition that he thought that all the way at the beginning, when space and time even disintegrate, well, maybe also physics disappears. Maybe the Big Bang, with the Big Bang, we've discovered something that's some sort of epistemic horizon. Science does not reach further backwards, he thought. And that kind of thinking of the Big Bang, that kind of modeling of the Big Bang is essentially what I've done in my work with Stephen Hawking. We've essentially modeled these earliest phases in which the distinction between space and time tends to evaporate, tends to dissolve in what we call quantum uncertainty. But that phase here, all the way back in the earliest moments of the universe, is in fact hiding a deeper level of evolution, a level of evolution playing out at the level of the laws of physics which Galileo taught are Platonic truths, immutable mathematical relationships. Today we think that even the laws of physics sort of morph and disappear. If I were to give you an abstract drawing of the earliest stages of the universe, it would look something like this. On top we have the laws of physics as we know them today. We go back to the Big Bang here, and what we see is that particles and forces lose their identity, they morph, they merge. What emerges is some sort of tree of laws that crystallized in these earliest stages. That's essentially the bottom line of the book that I wrote. And here comes the point. This evolution, at the level of the laws of physics, is playing out deep, deep in this invisible, unreachable era very early on in the universe. But not so for gravitational waves. Gravitational waves go right through. And each of these branchings that you see, such a branching, is essentially the birth of a new force of nature. It's a splitting of a force into two forces. Each branching, it's a huge change in these earliest stages of the universe. Each branching goes together with a burst of gravitational waves. Those primordial gravitational waves are the true fossils we're after with this Einstein Telescope project. These are the only fossils that they're still around. They still should fill the universe, but they're so weak, they're long wavelength, they're buried in the noise. Because I should point out that, I've given you sort of how we read these signals, that the first signal of 2015. But with Einstein Telescope and with the space experiment, we're going to be bombarded by gravitational waves from all corners in the universe. So the signal that we see is going to be a huge, huge mess. This is going to be, it's a superposition of all sorts of sources, and deep buried in this superposition will be, of course, the most interesting signals, those dating from the Big Bang. And so a lot of efforts in Leuven and elsewhere are devoted to developing tools, numerical tools, computing tools, data analysis tools to decode the gravitational wave mess that we will encounter once an observatory like Einstein Telescope comes online. So I will conclude, and I will circle back one more time to Galileo with his epistemic refinement. There are these rare moments in the history of science where we learn something, not just about the world, but about science itself. Galileo's was a moment, Einstein's theory was such a moment, and I believe this era, opening up with gravitational wave observations, is such a moment too. And something we might learn is the sort of core of what I advocated with Hawking and summarized here. On the left, you have Darwin's very first drawing of the tree of life. On the right, you have Lemaitre's drawing of the expansion of the universe. For a century, we've tried to explain these two very different levels of evolution on ontologically, epistemologically different grounds. Biology is about emergent laws, about evolution, history, chance, and so forth. Cosmology was always about immutable, transcendent, Platonic, fixed mathematical truths in the form of laws of physics. The deeper epistemic crux of the hypothesis that I put forward with Hawking is that this dichotomy was a mistake, that in fact, hidden in the earliest stages of the universe lies a deeper level of evolution. That level we can only unlock by developing gravitational wave observations. But it took Galileo and his contemporaries more than a century to sort out the solar system, from Copernicus in 1543, ultimately to Newton in 1687. Same thing is going to be happening today. This is going to take us a whole century to really develop the scientific potential that is hiding in gravitational wave observations. And I think that's also an important lesson. The story that I told you, from Einstein's mathematical equation to two multi-billion-dollar science projects, is a dialogue across generations. It's a dialogue across countries. It's a dialogue that takes us to timescales far, far beyond the sort of next level of innovation for next year. It's really something that such deep arcs, such long arcs, those are the kind of arcs that really, in my view, touch on our deeper roots as humanity. But that is not to forget that these multi-billion euro experiments are, of course, going far, far beyond the science. This is science, that's physics, but that is something different. This is something, I would say, requires a whole ecosystem, requires a whole ecosystem of stakeholders, of engineers, scientists, societal. It requires a broader scientific culture. To me, the key question, the fundamental question about are we ready to build Einstein Telescope in our region is really to what extent we can strengthen our scientific culture and come together in kind of the curiosity and the will and the power to sort of, there's a present for the next generation. And that's, I think, the key message here. So stay tuned. It's a moonshot project. It's a dream, but it may just happen. Thanks.